This is the par Inc. example, an example of how to use Excel Solver to solve a linear optimization problem. The par Inc. problem is what's known as a product mix optimization problem. We're trying, in this case, to decide the number of standard bags and the number of deluxe bags to produce in order to maximize contribution to profit. In this spreadsheet model, we have two sections, a parameter section, which I've highlighted here. This section only contains data, and we have a model section, which is where we calculate everything we need to know, such as contribution to profit, how much time is used in each of the four departments. Going back to the data section, you can see we have cutting and dyeing, sewing, finishing, inspection, and packaging. Four different operations that have to take place to construct each product. We have data here on the per unit amount of time in hours that it takes to produce a standard and a deluxe bag. So, for example, a standard bag requires 7/10 of an hour in cutting and dyeing, half an hour in sewing, 1 hour in finishing, and 1/10 of an hour in inspection and packaging. And we have similar data, how much time in terms of processing is required for deluxe bags in each of the four departments. We also have hours available in each of the four departments, 430 in cutting and dyeing, 600 in sewing, and so forth in cells D5 through D8. We also have the per unit contribution to profit for each type of bag. A standard bag gives us $10 per unit in terms of contribution to profit, and a deluxe bag gives us $9 per unit. So here, that's a description of the data for the problem. Again, the problem is to try to determine how many standard bags and how many deluxe bags to produce in order to maximize contribution to profit and not exceed the available capacity in each department. I'm going to press Control-tilde, and this will show us what is underlying each cell in this spreadsheet model. If we look at cell B16, we're calculating total profit, total contribution to profit, and that is the sum product of B9 and C9, which are the profit per unit, and how many we produce, which are these gray cells here. Incidentally, the gray cells are going to be the location for our decision variables, and in a moment we'll show how to use those gray cells for trial and error in terms of trying to find best standard and deluxe bags to produce. We also use the sum product function to calculate the hours used in each department. So you'll see we have cutting and dyeing, we do the sum product of B14 and C14. Again, those are the quantities, and B5 through C5, which are the cutting and dyeing per unit. And so that sum product gives us the number of hours used in cutting and dyeing. Similarly, we have used the sum product here for sewing, number of hours used in sewing, finishing, and inspection and packaging. Also, next to hours used, we have hours available, and here we've simply pulled down from the parameters section the relevant value for each of the four departments. And that allows us to just easily compare hours used and hours available. So I press Control-tilde again on my keyboard, and now we're back to where we can see the numbers that are calculated with those formula. So we have here in the decision cells one unit of one standard bag really, and one deluxe bag being produced. It gives us a contribution of $19. I use 1.7 hours cutting and dyeing, 1.333 in sewing, 1.667 in finishing, and 0.35 in inspection and packaging. So I'm nowhere near any of my limitations in any of the four departments. I can use this model then as a what-if model and say, what if I want to make 200 standard bags and 100 deluxe bags? You can see my profit has risen, the contribution to profit has risen to $2,900. and I haven't really hit any of my limits in terms of hours available. So I have capacity available in every department. So it's likely that this value, 2,900, is not optimal, and that the optimal product mix is not actually 200 and 100. We could try some more things, maybe change the 100 to 200. Now we see we still haven't exceeded any of our limits here. Profits gone up to 3,800. Again, we have capacity in every department, so it's not very likely that we're optimal yet. Well, rather than use trial and error, we can use Excel Solver to find the optimal levels in terms of production for standard bags and deluxe bags. So if I go to the Data tab, and to the right of on the Data ribbon, we have a group called Analyze, and in that Analyze group is Solver. If I click on Solver, the Solver Parameters dialog box appears, and it's through this dialog box that we convey to Excel the location of the objective function, the decision variables, and the constraints in the problem. So I'm going to click where it says Set Objective, click on this input box, and then I'm going to take my cursor, put it on cell B16 and click, because that's where I'm calculating contribution to profit. And notice that B16 appears in that input box. I can maximize or minimize. In fact, since it's profit, I'd like to maximize. Then by changing variable cells, that input box, if I click on it, I want to give the location of the decision cells. Here I'm going to click on the shaded cells, which is B14 and C14, and you see that that has been put into that input box. Of course, I could type any of this rather than drag the mouse, but most people find dragging the mouse a little easier. Next, I have to convey the constraint set, and here we have all the same types of constraints. We want the hours used to be less than or equal to the hours available in all 4 departments. So it's actually going to be fairly easy to enter these. We could enter them one by one, but as you'll see in a moment, I can enter them with one interaction with the dialog box. So I would like to add a constraint, so I click the Add button, and the Add Constraint dialog box appears. And what I'm going to do is click on Cell Reference and highlight hours used for each of the 4 departments. Notice it's put in B19 through B22, and the relationship is less than or equal to. I click on the constraint input box, and I'm going to highlight hours available for each of the 4 departments. Notice it has put in C19 through C22. So what we're conveying with this one use of the Add Constraint box is B19 must be less than or equal to C19. That's the cutting and dyeing. B20 must be less than or equal to C20. That's the sewing. And similarly for finishing and inspection and packaging. So I'm going to say OK, and you'll notice that in the dialog box now we have B19 through B22 must be less than or equal to C19 through C22. The other set of constraints are, of course, non-negativity. We have to make sure that we don't make negative amounts. So that's invoked by clicking this box that says Make Unconstrained Variables Non-Negative. It is checked. You want to make sure that is checked. We have a choice of methodology to use, and there are several here. This is a linear program, so we do want Simplex LP. LP stands for linear program. And now we are ready to solve. So I'm going to click the Solve button, and the Solver Results dialog box appears. And here it says Solver found a solution. All constraints and optimality conditions are satisfied. That's good. That means that it has solved the problem. You can keep the solver solution or restore the original values. We'd like to keep the solver solution. So I'm going to click OK. And now let's look at what's in the spreadsheet. Notice that it's replaced my previous values, and it's put 540 and 252 as the number of standard and deluxe bags to produce. Those are the optimal values. Those values give me a maximum contribution to profit of 7,668. In terms of our constraints, notice that cutting and dyeing, we are using all 630 hours available. Similarly, in finishing, we're using all 708 hours that are available. So we know from this that cutting and dyeing and finishing are binding constraints. We're utilizing all the capacity in those two departments. We also see that we have capacity remaining. We're only using 480 out of 600 hours in sewing and 117 out of 135 in inspection and packaging. So sewing and inspection and packaging are non-binding constraints. So we have solved the par inc problem using Excel Solver and have found the optimal solution.